Assalamu alaikum. This is lecture number 8, Physics 731. I'll discuss Green's function in terms of spherical and cylindrical systems of coordinates. Now let's first find the solution of a potential problem with a spherical symmetry. We know from previous lectures that phi for a Dirichlet type of boundary conditions is given by this form. A term consists of the distribution exists in the problem, and this is due to the boundaries. Now the problem I want to solve is the external problem, the interior problem, a sphere of radius r at zero potential. In the previous lecture, I solved the problem of two concentric spheres at zero potentials, and we found that the Green's function of such a problem is given by this expression, where A is the radius of the inner spherical shell and B is the radius of the outer spherical shell. Now, to get one sphere, we have to let A equal to 0 in the previous expression. So we left with one sphere of radius B. Therefore, a Green's function reduces to this form. Now, to evaluate, to find phi, we need, if we look at the first expression, equation number 1, we have to find dg by dn at the surface of the sphere of radius B. dg by dn is given by this expression, and since we are solving an interior problem, then n is pointing out. In the previous lecture, we solved an exterior problem where n is pointing inside. Now, evaluating the derivative and substitute for r prime equal b, we reach to this expression. Once you know what's phi at the surface, you can proceed and find the potential phi at any point inside the sphere. We know what's phi now, which is given by theta prime phi prime, and we know what's the normal derivative of g. So this is the final form of the potential inside the sphere. Now let's modify this by taking a distribution inside this sphere and kept this potential, the surface of the sphere, kept it at zero potential. Both the distribution and the sphere have the same origin, and the ring is located in the xy plane. They assume that the charge is uniform distributed over this ring. We have to write this distribution in terms of Dirac delta function, which is given by this. Now this is phi given by equation 1. Now at this point, g is known to us, but phi now is, which is theta prime phi prime, now is 0 at the surface of the sphere. So the second term is 0. We insert rho here, and then g, and integrate over the three parameters theta prime, phi prime, and r prime. Let's first evaluate the integral over phi prime, which is the easiest one. This term ylm star theta prime phi prime. We know that ylm is given by this expression. Now evaluating this integral, let's first evaluate over d phi prime of this integral. This is given by 2 by delta m 0. It means that m equals 0 will survive in the summation when we run the summation. Now substitute again in the theta phi part. We get this expression evaluating the integration over theta prime. This is theta prime. We get 2 by square root 2l plus 1 over 4 by bl of 0. Insert this result in the previous expression of phi, and we left with only integral over r prime. But Let's first change this into Legendre polynomial. We know that YL0 is this constant times BL of cosine theta. So insert this here and then evaluate this integral over R prime. We get this expression for phi, which depends on PL of x prime. Now, the smaller or the greater is the field point R or the radius of the ring. We have two expressions. We already did this problem in a previous lectures. Now, in a case of p goes to infinity, there is no sphere. We found that the solution, if we go back to this expression, let p goes to infinity, this is 0. Now we get this expression. We already solved this in the class. You can check your result. Another application is to put inside this sphere along the z-axis an uniform distribution, a rod of uniform distribution, which has this distribution lambda. As we did before, we have to convert this into Dirac delta function. So we have to write rho for this distribution, which is given by this, and then evaluating the integral. And again, you first do this integral over d phi prime, which means that m equals 0 will survive when we run the sum over m. Now doing all calculations, we finally reach to this phi. We can also find the surface charge density in this grounded sphere of radius b by taking the derivative of this phi with respect to r at r equal b. We get this expression. Now let's move to expand the Green's function in terms of cylindrical coordinates. We know this is the equation satisfied by the Green's function. The first thing is to write this in terms of the Dirac delta function and use completeness relation, and then use the same thing or write g in the same manner as we write delta, the Dirac delta function on the right hand side. Now this delta is given by 1 over rho, the Jacobian, delta rho minus rho prime, delta phi minus phi prime, delta z minus z prime. We write for this the completeness relation 1 over 2 by summation of ei m phi minus phi prime. For delta z minus the z prime, we write this integral form of the Dirac delta function, which is equivalent to 1 over pi 0 to infinity dk cosine kz minus z prime. To go from this form to this form, you have to break this from minus z infinity to 0 and change of variables, plus from 0 to infinity. It's easy to get this. Now insert these two expressions for delta z and delta phi in the left hand side of equation 1 and write g as a summation 1 over 2 pi square dk ai m phi minus phi prime cosine z minus z prime times the reduced Green's function. We already discussed such type of functions. Then go to the equation satisfied by the Green's function and find the Laplacian of the left hand side of the equation. That's del square sub x as vector x operating on g, and equate this to the right hand side of the Dirac delta function. Just if you do all calculations, just remember that this is the equation satisfied by this g sub m. To show this, now operate by del square in this equation, push this inside and do the derivative. We reach to this expression. Now equate the left hand side by the right hand side of the coefficients of ei m phi minus phi prime cosine kz minus z prime. We get this equation. the previous equation. This has solution for rho not equal to rho prime. It's a linear combination of I m k rho km is the modified Bessel functions, which is the Bessel functions of imaginary arguments. Now a linear combination is also a solution. Let us suppose that psi1 is a linear combination of I m k m with two constants a and b for rho less than rho prime, and for rho greater than rho prime assume that psi2, which is a linear combination of CIM plus DKM. Now to find A, B, C, D, the constants, we have to evaluate the boundary conditions and the properties of the Green's function. The first property is the symmetric, that Gm of k rho rho prime is Gm of k rho rho prime of rho prime rho, or it's a continuity of this function. Now let G sub m is written as psi1 of k rho lesser psi2 k rho greater, which is consists of two expressions. This is for rho less than rho prime, and this is for rho prime lesser than rho. The discontinuity equation, we have to go back to the differential equation, to this differential equation, and integrate from rho minus epsilon to rho plus epsilon. Evaluating this integral, we get this expression. Now, using this expression for Gm, we finally reach to this expression psi2 prime minus psi prime psi2 times this k equal this term, which is minus 4 pi over rho prime. This is the Wronskian, actually. It appears here. So the Wronskian is minus 4 pi over k prime times k. There's k here, not written. So if we look again at this equation, it is a Sturm-Liouville type. So we know that the Wronskian of two linearly independent solutions of this type is proportional to 1 over px. So we get this. Now to get an idea, let's take rho equal to 0 and rho equal to infinity for G sub m of k rho prime. In this case, psi1 reduces to this form, I sub m of k rho times constant. Psi2 is km of k rho. Psi2 reduces to this form. Now A can be determined from the Wronskian. We know that what's the behavior of I sub nu and k sub nu for small arguments and for large arguments. We discussed this in a previous lectures. Now, finding the Wronskian, we get minus 1 over x, and compare with the previous expression of w, we get that this constant equal to 4 pi. Now, insert this constant in terms of the Green's function, which is 1 over x minus x prime. The expansion of this which leads to 2 over pi 1 over pi square summation integration dk such times such functions g sub m of k rho prime. Now this is the final expression k rho lesser k rho greater. This is in fact two expressions. You have to break this into two terms. One for rho less than rho prime and one for rho greater than rho prime. We can write this also if we break the summation into three terms, m equals 0 and sum from minus infinity to minus 1 and from 0 to plus 1, we get this expression. We can do the same problem we did in the spherical harmonics, that taking two concentric cylinders at zero potentials and find the Green's function using this expression. We can also solve a problem 110, the one we used the reciprocation, the reciprocation Green's theorem. In this case, we can take in the spherical harmonics, we put a charge between the two grounded spheres or a charge between the two cylindrical spheres. This is left as an exercise for you to do. Thank you.